Question 1. Why does magnesium chloride have a high melting point? So maybe the best way of thinking about drawing it is firstly, is it consisting of a metal and a non-metal, which is the case. So it's got a metal and a non-metal. It's got ionic bonding. So we could draw a diagram of a general representation of ionic bonding, an arrangement of positive and negative ions, with negative ions surrounded by positive ions and positive ions surrounded by negative ions. So what have we got? We've got ions. So the possibilities are anything to do with looking for the word ions. Now what sorts of ions have we got? They're definitely strongly attracted together, so that sounds fair enough. But these two here are not attracted, and these two here are not attracted. What are attracted are opposite charged ions, so it's going to be D. Sodium chloride, again, typical ionic compound, again a reminder of metal plus non-metal. And it even says in the question, metal plus non-metal. What's it going to do? When does it conduct electricity? If we imagine that diagram here as a solid, for electricity flow we need charged particles which can move, which are either ions or delocalized electrons. Now we only get delocalized electrons in dual chemistry in graphite. Metal does also have them, but your syllabus doesn't mention those. So do these look like they can move? No, they're in fixed places, so not that one. When molten, that sounds valid. Oh, I didn't read the word not, so that's not true. Conduct electricity when molten, good, that's definitely true. Not conduct electricity when dissolved in water, that's also false, because if you imagine when ions are present and dissolved in water, they're floating around and able to move in every single direction. Which diagram is correct when we have a metal from group 3 with a non-metal from group 7? Let's go for aluminium, which is a classic example of a group 3 metal. It's got 13 protons, we'll have 13 electrons, and we could do a diagram, dot and cross diagram for a aluminium atom with 3 electrons in the outer shell. Now when it forms an ion, it could either gain or lose electrons, but metals lose electrons when they form ions to form positive ions, so it's lost 3 electrons. So we now need to think about what the charge is. It's still got 13 positive protons. In terms of electrons, it's got 10 electrons, 2 in the first shell, 8 in the second shell. So what's it got more of? It's got more positive protons. It's got 3 more positive protons than it has electrons, so the charge is going to be 3+. Something from group 7 could go for fluorine, for example. The arrangement of electrons in this would be 2 in the first shell, fill it up, and 7 in the second shell. When it forms an ion, it will need to gain electrons to obtain a full outer shell, so each one can gain 1 electron, and it will have a charge of 1- or just minus. So, and also to balance out the charge, for every aluminium 3+ ion, we would have to have 3 fluoride ions to make sure we have a neutral ionic compound. If we have a look at this diagram, something with a charge of 3+, it could either be that one or that one, so we can exclude B or C. If we look at this one has got a charge of -1. The one which fits is that one, so the correct answer is A. And you can see there are 3 negative ions with a charge of -1 to balance the positive charge of +3. Which one is most likely to be an ionic compound? The key properties are, if we talk about conductivity, does not conduct as solid, but does when molten or dissolved in water. So talking about a molten substance does not conduct electricity, can't be that one. Molten substance does not conduct electricity, can't be that one. Molten substance is a poor electrical conductor, can't be that one. molten substance readily conducts electricity, so it's going to be 4D. What's the correct name of MgSO4? If it was MgS, which is one compound you've met, that would be magnesium sulfide. If it's got metal and then two other elements where one is oxygen, for example like this, its ending, or the ending of sulfur becomes sulfate, magnesium sulfate. So that's A. Again, if you think about NaNO3, sodium nitrogen, and this one would be sodium nitride. This has got oxygen, this would be called sodium nitrate. So 8 implies 2 elements plus oxygen. Formula of copper 2 carbonate. Copper 2, the Roman numeral implies it's ACU2+. Carbonate, copper here, this means it's going to be either A or B. C is just carbon, or D I suppose, but carbon 8 means copper, carbon and oxygen, so we can exclude that one. Now, there are a variety of ways of trying to remember the formula for carbonate ion. Another one, which I haven't mentioned yet to you, is if you have a water molecule and a carbon dioxide molecule, two formulae you know, they can react together to form H2CO3. This is why rainwater is naturally slightly acidic. And there we have the formula of a carbonate ion. So from this we can deduce the answer is B. What's the formula of potassium nitrate? Obviously K is potassium nitrate. Just maybe learn it's CO3 minus, or maybe again think carbon and nitrogen are sort of to do with CO3 NO3. Obviously this one's got a charge of 2 minus. You could also learn the smallest tree in the world is, the nano tree, if you say 3 in an Irish type of way. So that reminds you it's NO3. The only possibility is D. This one here, if we do it in a slightly simpler version, maybe than last time, everything in group 2 forms 2+ ions. Everything in group 7, so here, forms -1 ions. If we did swap and drop, so as in writing the size of a charge for each of those ions below it, 2 and a 1, the formula would be 1 M2 2x, so it's mx2. mx2, the only one which fits that criteria is D. And again, we've got a charge of 2+ because metals from group 2. Everything in group 7 forms -1 ions. Ammonia, which is the correct diagram for it. We know nitrogen is in group 5 of the periodic table, so 5 electrons in the shell. It's combining with hydrogen, which has 1 electron in the outer shell, like so. So when they combine, we need to end up with everything with a full shell. Now, hydrogen can only form 1 bond, so we could try putting the nitrogen in the middle, bond it to 3 hydrogens. It's forming 3 single covalent bonds, so 3 shared pairs of electrons, like so. Now, we've said nitrogen has 5 electrons in their shell because it's in group 5. 1, 2, 3, 4, 5. So the answer for this one is B. The other way of doing it is, if you remember, nitrogen's in group 5. 5 electrons in their shell, it needs to gain 3. This means it forms 3 bonds. Hydrogen always forms 1 bond. If you imagine this as a sort of jigsaw puzzle, to fit it together, you would have a nitrogen in the middle with 3 hydrogens, like this, and again coming up with the diagram for B. Which of the following does not contain ionic bonds? So we're looking for ionic is metal plus non-metal. So we're looking first, let's cross out anything which is ionic. Silver, metal, oxygen, non-metal, so it's not going to be that one. Sodium, metal, oxygen, non-metal, not going to be that one. Sulfur dioxide, two different elements which are non-metals. Silicon dioxide, two different non-metals. Again, either one is a possibility. The only difference, or fundamental massive difference between the two, sulfur dioxide you may know as a gas which contributes to acid rain. That means it's got a simple structure, which we'll talk about a little bit later. Silicon dioxide, silicon's in group 4 and forms 4 bonds, and silicon dioxide has a giant structure. Silicon dioxide is effectively sand. So why has silicon dioxide got a high melting point? If it's non-metal, or two non-metals, and it's got a high melting point, we know that it must have a giant structure. What do we mean by a giant structure? We mean billions of particles which are either atoms or ions. If it's non-metals, it's going to be just atoms. So non-metals, obviously we could put here the word covalent. So we can exclude anything which has a word ionic. That's got word ionic, so we can cross that one out. Giant ionic, we can again cross that one out because it's got the word ions in. Giant, I've said it's giant. Also said it's covalent, so the best answer is 11B. Let's just check that 11C couldn't possibly. Simple molecular. If it's simple molecular, that means it's going to have a low melting point, not a high melting point. Question 12, let's see what information is provided in the question. Properties can be explained in terms of bonding and structure. The ionic compound, so it's an ionic compound, so thinking metal plus non-metal. High melting point. High melting point, again, anytime I think of high melting point, I think of giant structures. And here is a picture. In the picture, we can see it tells us the formula of a magnesium ion is 2+, the oxide ion is 2-. So structure, so it's got a giant structure, and the type of bonding found will obviously be ionic. So formula, the ions have the same charge, so the formula is just MgO. Why does it have such a high melting point? Why does it have a high melting point? Now, in an actual exam, you probably wouldn't get something a bit like A and C, but we can first talk about the structure. So you can say it has a giant ionic structure. And what does this mean? It has lots of strong ionic bonds which require lots of energy, like thermal energy, to break. Now, you could also, for this particular question, if you want, you could also just talk about what a ionic bond is, which is also equally valid. So you could say giant ionic structure and lots of, instead of strong ionic bonds, strong, then we'll go in here, electrostatic forces of attraction between oppositely charged ions. That would be an alternative to that bit there, just so you know where you sort of define what an ionic bond is. Why can it conduct when molten but not solid? So we need to talk about particles. There's 3 marks for it. So we could start off with the when molten. So when molten, what can move? Ionic compounds made of iron, so ions are free to move. And in solid, we need to talk about the ions not being free to move. Why are they not free to move? As solid, ions are in fixed positions and not free to move. Draw a dot and cross diagram for magnesium oxide. It tells us the electron configuration of magnesium and also of oxygen. So if we did oxygen first, two in the first shell, 6 in the outer shell. We know it's ionic, so that means it's separate circles, ions, so we think about charges. Then we draw magnesium. Also, there was a question way up there which reminded us that magnesium had ions of charges of 2+ and oxide ions of 2-. So we draw magnesium oxide, draw its shells. 2 in the first shell, 8 in the second shell, just using the information provided up here. Final shell has 2 electrons in its outer shell. Now, magnesium will obtain a full outer shell, so the 2 electrons from the outer shell will go from the outer shell of magnesium and be transferred to the oxygen atom. And we draw magnesium now with a charge of 2+, and the oxide ion with a charge of 2-, and we've got the 2 transferred electrons which came from magnesium here. So that's how we draw a dot and cross diagram for magnesium oxide. So the diagram shows 2 different forms of carbon. We can sort of see there's a fair number of atoms, so we try to count it. I go quickly. There's quite a lot there, so that tries to indicate that this is part of a giant structure. Not all of it is shown. Again, we can sort of see a regular repeating pattern, and we can imagine it continuing in each direction. So again, we could look at diamond first. We could choose some select atoms, and we can see that some carbons shown are bonded to 4. Now in reality, each carbon is bonded to 4 other atoms in this sort of tetrahedral arrangement, but basically, for trying to simplify it, they haven't shown all of it. We've got graphite here. Again, we can see carbons, and if you look at lots of carbons, they're forming 3 bonds, which is true. Graphite has 3 bonds per carbon, and diamond has 4 bonds per carbon. Again, in both diagrams, we can see solid lines. Solid lines represent, and it's a single solid line, so this represents a single covalent bond. Anything not shown in graphite is between the layers are weak forces of attraction, and that's between the layers. So what type of bonding is shown in both things? We've got covalent bonding. Why does it have a very high melting point? So we need to talk about structure and bonding. This is usually what we have to do. So we can say it's got a giant covalent structure. So giant covalent for one of the 4 marks. Then we can think about bonds themselves. They're going to be, and has lots of strong, let's just use the word covalent again to really reinforce the sort of type bonding, covalent bonds. And then what do we need to do if we're heating something up a lot? We're going to break bonds, and it's going to require and lots of energy is required to break bonds. This apparatus is used to determine the amount of oxygen in air. We've got excess iron wool, so excess means more than necessary for the reaction. We also have air, which contains 21% of oxygen, 78% of nitrogen and water. Now when we have iron, oxygen and water, rusting can occur. So it's record the initial volume, then when it becomes constant, as in the water stops rising up, it records the final volume. How long might it take for rusting to occur? If you think about your bike chain or something, if you blink, it hasn't suddenly rusted. Even after a minute, it still hasn't rusted. But if you leave your bike maybe outside for a week, it probably will have rusted. And again, that's roughly how long you left to experiment when you carried it out. So apart from changes to the level of water, what other might be made as an observation at the end? Let's have a look back at this. We've got iron. How do we know iron's gone rusty? Again, I find referring to my bike chain is helpful, but maybe not everyone cycles. So iron has gone rusty, and you could give a description: this, turned brown, because all metals can be described as grey and shiny, apart from two metals, which are gold and copper, which can be described as sort of brown metals before they do anything. The teacher adjusts the apparatus before recording the tube. Explain the changes that he makes. So if we look at this diagram, these little lines represent the scale which we use to measure it. At the moment, you can see if we were trying to take a reading from here, it wouldn't be ideal. So what do we need to do? We need to hold a tube upright or hold a tube vertical. And why do we do this? So that the scale can be read correctly. And this means that the volume recorded is going to be accurate. Calculations. Calculate the percent of oxygen in the air after the first experiment. Now you've got some examples here. So you could always try to work out how 18% was obtained. You could also learn an equation which might help you. So the equation is change in volume. And the change in volume is due to the amount of oxygen which has now gone from being a gas to being incorporated with iron and a bit of water in rust, divided by initial volume. So 32 minus 26 over 32, and obviously it's percentage, so it should be times by 100. So what do we have? This gives us 18.75. Now all the other data is recorded to just 2 sig figs, so I would give this as 19%. So this bit is a bit of a interesting bit of question, and it's only ever turned up once, so if you're not so sure about it, it's not something worth worrying about now. All the volumes of gas recorded, or initial volumes, so 32 minus 26, that's got a volume of about 6, that's a volume of 6, that's a volume of 5, that's a change in volume of 4. All these changes are very small. Also the values are only recorded to the nearest centimetre cubed. So the problem is, if you values say 25 or 26, or 26 versus 27, a small error may make a very big difference in the percentage of oxygen calculated. So volume change is small, and so the problem with this is, so a small error in making measurement will give a very different value or percentage of oxygen in the air. Now, what would happen if it was left for a shorter period of time? If you imagine your tube of air here, and I'm just trying to show the sort of progress of reaction. So we start off with water below, and we could also have in that tube, we could have some oxygen. We could also have some nitrogen. I'm trying to draw these little pairs, but my screen isn't quite accurate enough. So we start off with something like this. So we start that. Now what's going to happen during course reaction? Obviously, it might be worth drawing some grey iron wool in place. Here's my iron wool there, there, and there. Some of the oxygen is going to react with the iron. So we start off with, I'm sorry about sort of rather random pauses there. Like that, right. So we start off here. We've got 2 molecules of oxygen. After a little bit of time, some of it will have rusted, so the volume of liquid or water will have gone up slightly. So there will be less oxygen, so we carried out the calculation here. The change in volume will be smaller, so the calculated percentage would be smaller, so maybe we'd have 10% for this one. At the end, we're probably going to get close to obviously 21%, and the volume of liquid will be here. There's no oxygen left, and we can see I've tried to do a bit at the top to try showing the iron having rusted. So short period of time, imagine after a second, if we try doing a calculation, we find a much smaller percentage. So percentage of oxygen calculated is smaller, and we have to explain why, and this is because some of the oxygen is unreacted. So that's just that little bit there. Next one, larger piece of iron while it's used. This is why I was making a point earlier about excess. So we've got an excess of iron. There's already enough iron for all the rusting to occur. So there will be no change in percentage of oxygen calculated as iron wool is in excess already, so adding more excess will make no difference.